Okay. Okay, here we go. I'm nervous. Okay, so this one right here, what is it?
A parabola.
It's a parabola, which means what kind of function is it? Quadratic. Number 6. Now we didn't fill out this top part right here because that's the chart that I just put on the board. I'm hoping that the chart helps a lot more than this fill in the blank would. Number 6. What kind of function is that? Number 7. It's linear. Just a line. And number 8. If it were exponential, it would be going flat right here. It's not. If it were quadratic, it would be going back up, right? This actually is an x cubed, which means it's a cubic. And that is not something we cover in this course. So out of those 3, this would be none of them.
I love the fact that it's
Good. Okay, so the next chunk of examples just goes through a lot of different scenarios. It gives you a graph, it gives you a table, it gives you an equation or a scenario, and you have to decide which of those 3 it is or if it's none of them. The instructions ask you to list 2 reasons why. Just list 1 because I have a hard time thinking of the second. So number 1, what is it and how do you know? Yeah. It's a straight line, so it's linear. Number 2. Now the first thing, if I'm given a table that I want to look at, I have a tennis tournament. There are certain rounds, round 1, 2, 3, 4, 5, and there are a number of players left, so it looks like it's an elimination tournament. The rounds would be my x values. The number of players will be my y values. So the first thing you look at is the x values increasing or decreasing at the same rate? They are, right? So you just have to check for that first. That doesn't mean it's linear. That means now we can look at here. Look at those 2. What's happening? Those 2, what's happening? They're all dividing by 2, right? So this is my common multiplier, which means it is exponential. Very good. Yes. Because it's decreasing, not at a constant rate, but by a constant multiplier, I would call it exponential. If I'm dividing 2 every time, it's going to be exponential. Look at the next one. Y equals 4x. No, just divide by 2. We're only going to give 1 reason. Yeah. Okay, number 3. This one. It's linear. And how do we know? Look at this exponent right here. It's a 1, right? So the reason would be degree 1. Yeah. There's no what? No, I would say degree 1. Because there is, it's just not showing. So if the equation looked like this, just kidding. If the equation looked like 4 to the x power, do you see the difference between the 2? This one, the degree, there isn't one because it's x as the exponent, so this one would be exponential. This one, just 4x, that's a line. The slope's 4, the intercept's 0, just a line.
You know how exponential can be decreasing or increasing at a constant rate?
Not at a constant rate. It has a constant multiplier, the same multiplier. When you say rate, you're thinking that you're adding 4 or subtracting 4. That's a little bit different. So a multiplier is different than a rate. Yeah, this is a totally different problem. Yeah. Number 4, this function is decreasing at a constant rate. This word right here is the reason why we know it's linear. So when I say a constant rate, that means I'm subtracting 4 every single time, or I'm adding 10 every single time. What about this one? Let's start comparing what the points are first. Okay, so look at this one right here. So to get to that next point, I went up 1 and I went over 1, right? Now let's look at the 7. To get this one, we went up 2 over how many? 4. So now I'm thinking it's what? I mean, with only 2 points, it's really hard to tell, but 1 and 4 make me start thinking parabola, right? Looking at the next one, it's over here at 12, up at...
How does 1 and 4 make you think about it, right?
Because 1's a perfect square and 4 is a perfect square. So when we were doing the quadratics and we said the general pattern was over 1, up 1, over 2, up 4, the next one would be over 3, up what? 9, perfect square. So is it, we did go up 3, right? How far over is it? 9. I would say this one's a sideways quadratic. No. And the reason would be, I kind of showed it in the picture, but 1, 4, 9, those are all perfect squares. Nothing goes sideways. This would be the inverse of a, man, that's a different lesson. I would call this quadratic. Yeah, if you, yeah, that. This one just looks like the range has been restricted to only do the positive ones. Yeah. What about number 6? A person's height as a function of a person's age from 0 to 100. So what happens when you're born? That first year of a baby's life, they like triple, right? Born at 6 pounds, not my children, but born at 6 pounds. My kids were 10 pounds, by the way, when they were born. All of them. Almost all of them. They were big old, like, fat babies. But they're born 6, 7, 8 pounds, right? And when they're 1, usually babies are about 20 pounds. But do I triple in weight or height? I guess this is a height problem. But do I triple every year until I'm 100? Those 100-year-old ladies are certainly not 300,000 feet or whatever, inches. It's not going to keep going forever. What happens? I'm born, I jump up, and then I level out, right? I haven't grown since I was 16.
Sometimes you even start going back.
And sometimes Grandma has gravity take effect and she goes down a little bit, right? Darn it, poor Grandma. So, clearly it's not linear, right? It doesn't shoot up and keep going forever. It doesn't go up and come back down unless you were talking a lot longer than 100 years. I'm going to say this is none. Because none's an option, right? It's possible not to have any of those. Poor Grandma. All right, moving on. Number 7. This one is not in standard form, but you still could look at the x's. You gotta be careful because I'm recording, so if I call you out by name, it's gonna be on my internet forever. Right? No, that was before we started recording. Okay, this one. This is not in standard form, but I still could get y by, like, if I got y by itself, would this change at all? No, the power on this is still what? The coefficient's 3. It's still a 1. That means it's linear. And my reason? My degree is 1. Number 8, we have a table again. We want to look at the table. Is my x values increasing by the same amount? 2, 0, yeah. Now look at the y values. How fast are they jumping up or jumping down? From 23 to 5, I've done what? gone down 18. From 5 to 13, I've done what? Down 18. 13 to the negative 31, down 18. This is a constant rate, right? So this one would be linear. My reason why? It has a constant rate. Compare that with number 9. Check your x values first. What's going on there?
It goes up 7. Or no. Then it goes up 6.
12 the first time.
Oh, yeah, 12.
So from 62 to 74, that's up 12, and then down 4, and then down 3. So these are all scrambled, right?
Yeah.
So why don't we take a second and just reorder them? So my first one would be 53 and 4. My next one is 58 and 7. 62 and 6. 67 and 11. 70 and 9. And 74 with 13.
We can do that, we can just go off this side and do it.
Or I'm sure. Yeah, that's no problem. Okay, so what's going on here? This is up 5, up 4, up 5, up 3, up 4. So it looks like they're still all over the place, right?
Oh, no.
They're not going up by a constant. If we were to find the slope, I mean, this one's going up 3 and then down 1 and then up 5 and down 2. It's all over the place. I'm saying this is none. Number,
So since it's none, you wouldn't be able to go off that?
if you graphed it, it would just kind of look like a bunch of peaks and valleys.
So it would be like a scatter.
Kind of, yeah. Yeah. Or it would look like a business that's like market, or they're showing a graph of their income and how it just kind of goes up and down. Yeah. Number 10, the number of cell phone users in Centerville as a function of years, if the number of users is increasing by 75% every year. This is my multiplier, right? So if you flip to the very back on the chart that you created, in the exponential column, did it say something about a percent of increase or a percent of decrease? It did, right? So this would be exponential. My common multiplier is 75%. Or if we compare this to what we did last time, the 75% would be the growth, what, rate? Which means my growth factor would be 1.75. Right? Is that okay? Yeah. Yeah, the R stands for rate. Number 11, what does this one look like? It looks like exponential. You probably should check the points to be sure. This one right here is at 1. This one is at 2. The next one is at 4. Then 8. So what's my multiplier here? My multiplier is 2. Exponential because my multiplier is 2. Number 12, the time it takes you to get to work as a function of the speed at which you drive. Now this is tricky because if I were driving on the freeway from Cedar City to St. George and I had my cruise control on at 75 miles per hour or 85 miles per hour, that would be linear, right? I'm going 85 miles per hour the entire trip. I don't slow down, I don't speed up, I'm going 85.
But if you like follow speed limits.
But my commute to work, I pull out of my driveway, I stop at the stoplight, I turn left, I stop at the stop sign, I turn right, I pull up the hill, I stop, I turn left, I wait for cars, I see a cop, I slow down, right? I would say it's none because you're constantly changing. Sometimes you're going fast, sometimes you're slowing down. I'm going to call this one none.
Too unpredictable.
Yeah, if I had to give a reason why, I would just say that the rate of change is changing. Yeah. Okay, number 13. How do you know? So my reason, degree 2. So it's quadratic. Number 14, each point on the graph is exactly 1/3 of the previous point. This right here is the what? It's the multiplier. To get my next point, I take the one before, and it's 1/3 of it. Times 1/3, times 1/3, times 1/3. So this one is exponential. We're almost done. Compare that with number 16. Sorry, I know it's slow. This is what this means. My first number, so f of 0 is 1. And here's what this means. To get my next number, I take the current number and times it by 2/3. So every number that comes next, I take whatever I'm on and multiply it by 2/3. So this right here again is the what? Man. So it is exponential. Last one. If I were listing my numbers, my first number is 7. That's what f of 1 means. My second number is 7 again. And then what does this mean? To get my next one, I will take the one before and the one before that and add them together. So to get the third term, I'll take the one before and the one before that and add them together. So this would be 14 because 7 plus 7 is 14. The next one would be 7 plus 14, which is 21. And then 14 plus 21 is 35. Add those together, you get 56. Add those together, 91, and so on. Now, I'm not adding the same thing every time, right? It kind of sounds like the Fibonacci sequence, right? 1, 1, 2, 3, 5, 8, except for we started at a different spot. 1, 1, 2. Oh, this is 7 times the Fibonacci sequence. Interesting. So to get my next term, I'm not adding the same thing every time. I'm not multiplying the same thing every time. And if I find my difference, it's probably not going to be 149, right? I'm going to call this none. To get the 14, we take those two and add them together, we get 14. Because of this right here. So you take the previous term. Oh, so this is just talking about term, so not n anything. So n minus 1 means the previous term, and n minus 2 means the term before that. That's what that means. The term after. Yeah. Okay, flip your classwork really quick. I want to do a few more of these. Have I already gotten answers on here? No. Yeah, flip to this little chart here on the very last page. It's kind of hard to see. If I get any lower, I don't know how it's going to focus. So it's the very last chart on the bottom corner. On this chart, it's the same thing, and they're very small. I'm sorry, again, we just used scissors and cut them all up. So, I want to know, is it linear, is it exponential, is it quadratic, and you just can put L, Q, and whatever the other one is, E. So this one is what? Linear. Ooh, my hand doesn't fit underneath the microphone. Linear. The next one is, now this one could probably go either way. It doesn't quite look exponential. It's going up really slow. It could be. If I drew this other part right here, it could be quadratic. But I could see justification for both of them. So which one do you want to put? Quadratic. I've got to back this up just a little bit. The next one is linear. The next one, quadratic. Okay, row 2. This is quadratic flipped on its side, right? This one is the next one. If it had a y equals, it would be a linear. No, I'd say it's linear. What about this next one? It has an x squared, so it's quadratic. The next one, y equals 4.7. This is one of those flat lines that we looked at when we were doing piecewise functions. So this is linear still. What about the next one, pi x? It's still linear. The pi does nothing except for tells me how fast my line is growing. So I add pi every time. It's linear. It's still a degree 1. Look at the next one, 4 over x. It's going to be completely different. If I'm graphing 4 over x, hold on. Oh, kind of hard to see. It's not very bright. Yeah, you can't see it at all. Hold on, backing up. It's probably because it's dark in here. So 4 divided by x, when I graph it, oh, booger, you can't see it.
Oh, it's like,
Can you sort of see it?
Yeah.
It's too dark in here, I think. There you go. Can you see it now?
Oh.
So what's happening there?
There's 2 different
It's
things.
like I'm going down on this side, I'm going up on this side. This is none. That's not exponential. I'm going to call this none. That's what a graph when you divide by a variable will look like. We spend almost an entire unit in secondary 3 looking at graphs like that. A little bit, yes. So this one, what are we going to put? None. What about this one? Again, I've got that 2 times x to the first power, so it's linear. The next one, 4 times x minus 1. It's right here. If I were to simplify that, it would be 4x minus 4. X is not an exponent. There's no squared. It's linear. But on this one, the x is the exponent, so we can say it's exponential. The next one, 2/5 is the slope. X to the first power, linear. The next one, apparently they're all linear. What about the next one? If I were trying to get y by itself, what would I have to do?
Divide by 5x.
So this would be another example where we have x on the bottom. What happened up here when we had x on the bottom?
That's none.
It gave us this crazy graph, right? It's going to happen again. It's going to be none. The next one, you've got y plus x equals 4x. So if I subtracted x, it would be y equals 3x plus 5. Still degree 1, linear. What about the next one? I know it's small, hard to read. It has an x squared, so it's quadratic.
Isn't that what the x cubed?
And this one looks just like the x cubed that we saw in our notes, so this would be none. Okay. The first couple questions. Yep. Okay, look at that. 16 of them done for you. With you. Not for you, just with you. Okay, the last thing really quick that weren't part of your notes. Let me find a new classwork that doesn't have a folder. No, that is true. What's that? Yeah, I know. And if I had okay, the last thing I want to look at is how do I tell whether situation A or situation B has a greater rate of change? Oh, focusing. So how do I tell what the rate of change is in part A, or number 1? If I'm going from a negative 48 to a negative 43, sorry, with me? It's the page right after the graphs. It has this like roller coaster look. I have no idea what that is. I think it's a roller coaster. I'm not sure. Okay, so if I'm going from negative 48 to a negative 43, what change? It's going to go up 5, right? From here to here, it's what? Up 5 again. And from here to here, it is also up 5. So what's the rate of change on part A? 5.
So that's linear?
It is linear, yes. But our question is identify whether situation A or situation B has a greater rate of change. So now, how do I find the rate of change if I'm talking about a graph? I'm looking for the slope. Do you remember how to find the slope of a graph? You find one point, and then your next point, and you kind of make it into a triangle. Remember that slope is rise over run. So we go up 6 over 1, which means the slope is 6. So which one has a greater rate of change? B. I want to do 3 of these with you. Yeah, I just circled B. Looking at number 2, you can kind of tell based on the picture which one looks like it's going up faster. Yeah, this one's going up faster. If we had to decide what the multiplier is, though, because these are both exponential, looking at this point, so this point's a 1, this point's a 2, this point is a 4, this point is an 8. What's going on there? The multiplier would be what? 2. This was an add 5, add 6. This is going to be a multiply 2. This one, I'm here at 1, and my next point is where? I think it's actually 5. So and then the next one's not even on the grid. So this would be a multiply 5. Which one has the higher rate of change? We already said based on the picture. But if I had to prove it by showing some numbers, 5 is more than 2. The last one I'd like to do with you is number 4, and then I'll give you time to work by yourself for a minute. Number 3 confuses you? I'll come around and I'll help. I just wanted to look at number 4 really quick. Looking at the B situation on number 4, what's happening between figure 1, figure 2, figure 3? From here to here. From here to here plus 2, right? Excuse me. Okay. Now look at situation A. What's happening there?
Oh, it's plus 2. They're equal.
It also looks like it's a plus 2, so you have to look closer at one of them.
You always look at Y.
No. Look at the X on part A.
Well, it's plus 4, but the y is skipping every other one. Yeah.
So the y is going up by 2, but how long does it take to get from one to the next? It takes 4 x's, right? How long does it take to get to the next here? 1. So to go from figure 1, figure 2, only takes 1 figure. If I were to draw all of these out, it would take 4 to get from. So which one's increasing faster? Because this one, if I took it as a 7, if I were to write in 7, 8, 9, I don't get to the 15 until I get to 10, right? So if I had the 7, what would it be? It would be like 13.5, and then 14, and then 14.5, and then I get to my 15. So really, what's my rate of change here?
Like 1/4?
1/2? Going by half. So because it takes longer for me to get from the 6 to the 10, I'm going to say this one's going up faster. Again, yes, it's plus 2, but it takes 4 steps to get there. This is plus 2, it only takes 1 step to get there. All right, you have 15, 17 minutes left. There is a couple more that I'd like to look at together, but I want you to have a chance to look at them first. So maybe if you want to come back in about 12 minutes, we can finish these up. So for the next 12 minutes, please work. Here, we'll stop this.